chapter 11 deals with the theory underlying chemistry, theory of chemistry. It's called quantum mechanics. So we can take a look. This is Atomic Theory Part 2. And let's just preview the chapter here. There's some stuff about light. Properties of light. Well, quantum mechanics, the development of quantum mechanics is pretty interesting. Because quantum mechanics came from the observation of unusual light patterns. And why light is important. So let's talk about light first. Light is, we don't think of it as matter. We think of it as energy transferred in the form of these oscillating up and down electric and magnetic fields. So we have different types of light. Normally when people think of light, they think of the visible spectrum, the rainbow colors. When we add up the rainbow colors, we get white light. So the sun emits white light because it emits all the colors in the rainbow. But the sun also emits infrared, ultraviolet light. There could be some X-rays as well. And so those aren't visible to the naked eye, infrared, UV, X-rays. But those are the exact same. Infrared is a little lower in energy, UV is a little higher in energy than these. This is just transmission of energy via oscillating electric and magnetic fields. Okay, when we have oscillating fields, we can characterize two things with an oscillating field. One is the wavelength. The wavelength is the peak-to-peak distance or the trough-to-trough distance. So this would be one wavelength here. Now the light isn't static, it's moving. In fact, it moves at the speed of light. The speed of light is very fast. It's like 3 times 10 to the 8 meters per second. And so light is moving very fast. As light moves, let's say this light is hitting you, then what you're going to feel is you're going to feel some oscillations in the electric and magnetic field. And so, all the light, whether it's gamma rays or radio waves, all these light forms move at the same speed. The difference is the wavelength and how fast these oscillations hit you. How fast the oscillations hit you is called the frequency. The frequency is the peak to peak, that is one cycle. How many cycles in a second? And so how many of these peak to peak cycles hit you in a second is huge. So for example, if we look at radio waves, the radio waves, they have a wavelength on the order of like a kilometer, let's say. Is that AM radios around a kilometer wavelength, 10 to the third meters. But that hits you at thousands of cycles per second because light is moving so fast. FM radio waves have wavelengths that is a peak-to-peak distance of, let's say, 1 meter to 100 meters. If you're looking at FM radio, 1 meter to 100 meters long, the distance between the peaks, and yet 1 million of these cycles will hit you in a second. That is, it's 1 million hertz or megahertz. FM radio is megahertz, AM radio is kilohertz. So megahertz is 1 million cycles per second, just up and down like this. Okay. What an oscillating electric field is it's going to oscillate like this. Okay. And what you're going to feel okay, the electric field's oscillating, so it goes, let's say, plus, minus, minus. And so what that's going to interact with is going to interact with charged species. like electrons, not so much protons. And so let's look at an antenna, radio antenna. If we look at a radio antenna like this, then a radio antenna is made up of, typically it's made up of metals. And the metals are going to have some nucleus here, let's say, with some positive charge in the nucleus, protons. But one thing about metals is the electrons in metals are kind of loosely held. And so these electrons are pretty loose. And so if a radio wave hits the antenna is going to experience an oscillating field like this, up and down. And so the nuclei are kind of massive, they're heavy. And so the nuclei are heavy, so they don't really oscillate with the field. However, the electrons are light, and the electrons being light, the electrons will start to oscillate with the field. And so if a radio wave hits this, then the electrons in the antenna start to oscillate up and down. We call that exciting electrons. And so primarily light is going to interact with the electrons in matter. Okay. This is called spectroscopy. Spectroscopy is equal to the interaction of light and matter. So we have lots of different spectroscopies out there, depending on what energy light you're using. We have radio wave spectroscopy. This would be like long radio waves or TV. Microwave spectroscopy, infrared spectroscopy, visible spectroscopy, ultraviolet spectroscopy, X-ray spectroscopy, gamma ray spectroscopy, depending on what you're hitting it with. And so let's just look in general what the different energies of light do to matter. And so basically, let's just summarize that light is these oscillating electric and magnetic fields that are moving. They have a velocity or a speed. Speed and velocity are the same. And the velocity is 2.9, what is it, 2.98 times 10 to the 8 meters per second. 3.0 or 2. Actually, it's been a while since I used that. Let's look at the speed of light. That's 3. Yeah, I'm looking forward to a little bit more than 2 sig figs. We want this 3 sig figs bar. 2.998. 2.998 meters per second, or 3.00. So 2.998, that's the 4 sig figs, but we're probably okay at 3 sig figs. 3.00 times 10 to the 8 meters per second. The speed of light. That's that's not exact, that's approximate. So that's moving very fast. Is it 10 to the 7? 300 million meters per second. That's how fast it's moving. So if this light hits you, it's hitting you at 300 million meters per second, but do you feel it? Do you feel it? You don't really feel it because white light doesn't have any like rest mass. But certain parts of your body will feel it, like the electrons will feel it, depending on what type of light it is, what energy of light it is. And so this is a constant. This is in a vacuum, actually, a constant vacuum. That's how that. And so all light, no matter whether it's gamma rays or radio waves, radio waves move at the speed of light as do gamma rays. The difference is in the wavelength and the frequency. And so we should take a look at the light here. The highest energy light, and this is what you should know the energies of the light. What is the highest energy? Gamma. So let's take gamma. Gamma has a symbol like this. The gamma. Gamma rays. That's the highest energy. This is going to have the shortest wavelength, shortest lambda. It has the shortest lambda. Lambda is the wavelength. This is the symbol we give to wavelength. Wavelength. Just the peak to peak distance. If we look at the wavelength, it's 10 to the minus 16 meters to 10 to the minus 14 meters. You know, if you think about it, how big is an atom, roughly? (10 to the minus 10 meters). So that's even smaller than an atom. This wavelength is smaller than an atom. That means it's going to have the highest frequency. And so it's going to have the shortest wavelength, the highest frequency. Frequency, we give this symbol. This symbol is called mu. This one's lambda. So it has the shortest lambda, highest mu. Mu stands for frequency. Gamma rays are also going to have the highest energy. Highest energy. So let's say you have your radio antenna and you blast it with gamma rays. What's going to happen? You know what's going to happen? What's going to happen are the electrons are going to get too excited. If the electrons get too excited because they're oscillating, you know, the field comes in. It's like waves, you know, and the electrons are like little boats floating on the surface of the waves. But if these waves are too fast, too violent, what's going to happen is the electrons are going to start oscillating like this, and the electrons are going to get knocked off the atoms. When electrons get knocked off the atoms, we call that ionization. And so gamma rays are called ionizing radiation because what happens is they'll just completely knock electrons off matter. So this is ionizing radiation. So this is ionizes matter. Whereas radio waves, you know, radio waves are mellow, much more mellow. Even though they're megahertz, 1,000,000 cycles per second, these are way higher. But you know, radio waves, the electrons just get excited. They don't get knocked off the atoms. They just get excited. So we got gamma rays, and then we got, at the bottom, we got the radio TV waves. Put those down here, and then in between. So below gamma rays comes what? X-rays. And then UV, which is ultraviolet. And then visible light comes in. Now there are different energies of visible light. You know, what is the highest energy color of visible light? It's not red, it's the other end. It's violet. If we look at the colors of the rainbow, the colors of the rainbow go Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. So Roy G. Biv. Violet being the highest energy. So violet's going to have a shorter wavelength than red. So it goes violet, indigo, blue, green, yellow, orange, red. Roy G. Biv. And so violet will have shorter wavelength, red will have longer wavelength. Violet will have higher frequency, red will have lower frequency. Violet will have higher energy, red will have lower energy. So it's visible. And then, ultraviolet is beyond violet. What's beyond red? Infrared. So this is infrared. Infrared is just beyond red. Infrared is invisible. Violet is invisible. So violet's on the other side. Ultraviolet's on the other side of violet. Infrared's on the other side of red. Infrared's lower in energy. Infrared has wavelengths on the order of centimeters, and frequencies in the gigahertz range. Gigahertz. What's lower in energy than infrared? Microwaves. Actually, microwaves are on the order of centimeters. Gigahertz. Infrared. We'll talk more about that. So microwave is lower in energy than infrared, followed by radio TV. Radio TV, these are the lowest energy visible light. And so you should know, but people often get confused as infrared and microwave, where to position those. So it's going to go gamma, X, UV, visible, and then visible goes violet to red, infrared, microwave, radio TV. Radio TV is going to have the longest lambda. We're going to have the longest lambda down here, longest wavelength. We're going to have the lowest frequency, and the lowest energy down here. So what radio waves can do is they can excite electrons in metals. It's not hard to excite electrons in metals because electrons are kind of loosely held in metals. That's why they're easy to oxidize or easier to oxidize. Excite electrons in metal. A little higher in energy, microwaves. What can microwaves do? If you put metal into a microwave, do you know what happens? You ever put metal into a microwave? Sparks fly. So maybe it's the electrons are getting too excited. The electrons are getting too excited, they're going to get ionized. So this could, microwaves can ionize electrons in metals, ionize electrons in metals. But do you know how microwave ovens work? Microwave ovens have enough energy. Actually, somebody left their models here. They have enough energy to rotate small molecules. Because if you think about it, water is not water, but water has a. If we look at water, let me draw it like this. The hydrogen ends of the water are positive, and the oxygen end is negative. And so what happens is these water molecules, they're neutral in the sense that they don't have any charge, but the way the charge is distributed, this negative charge cancels out the positive charge, but still there is some. When we look deeper, there is charge here, and that is the hydrogens are positive. It's not fully positive, so we use this little delta symbol here. Delta just means a partial positive. This would be a partial negative up here. This is the color coding scheme. Usually when we think of positive, we think of red, but they decided to put red as negative, whoever that is. But anyway, so the molecule, this is what we call polar. The molecule has some charged regions in it. And when you add up all the charged regions, it comes out to be neutral. But nonetheless, if the molecule's like this and you have an oscillating electric field, then the molecule is going to oscillate with the field. Let's say, all of a sudden it's positive, so it's just like this. Then it goes negative, just like that. And so what happens is microwaves can cause the molecules to rotate like And so microwave oven will cause water molecules to rotate. As they rotate, they're going to collide and they're going to generate heat. It turns out there's a specific amount of energy that's required to rotate this. And so microwaves can ionize electrons and metals and rotate small molecules. Rotate small molecules. If it's a big molecule, then it's going to need a little more energy to rotate that. Look at this microwave. Now, infrared causes this is called a bond. Between hydrogen and oxygen, these atoms are bonded together. That is, they're held together. And so what infrared does is it causes vibrations, causes bonds to vibrate. Microwaves don't have enough energy. And so you look, there's a positive end and a negative end. So if you have an oscillating field, the bond is going to start to vibrate like this. So oscillating field, if it has enough energy. So bonds vibrate. In other words, we get vibrations with infrared. What visible light does, visible light actually excites the electrons in the atoms themselves. It will excite electrons in matter. And so visible light excites electrons in matter. Ultraviolet gets them too excited. And so there's electrons in the hydrogen and oxygen atom. And it's okay if they get excited, but if they get too excited, what happens is things can break. And so what ultraviolet does is it causes bond breakage, causes the atoms to separate. Here. And so if this bond here gets too excited, vibrating or whatever, then eventually it's going to break. The hydrogen breaks off the oxygen. And then X-rays ionize matter like gamma rays. So they can excite the electrons too much. It causes ionization to occur. Over here?
Yeah, all the way to the right.
All the way to the right?
Yeah, when you wrote right there. Yeah.
Causes bonds to vibrate, or just vibrations. Infrared is vibrations. Microwave is rotations. Microwave rotations, infrared vibrations. Microwaves can ionize electrons in metals, because metals have easily ionizable electrons. That's why they're good reducing agents. Easily ionizable electrons. So, well, how do we generate light? You know, how's light generated? How do we make light? Well, the sun is a gigantic light bulb. Right? The sun was a gigantic light bulb. What is the sun made out of? What the sun's made out of? So if you look at the sun is emitting light. Typically, what type of light does the sun emit? It's like a lot, all these, I think. But it doesn't emit a tremendous amount of X-rays and gamma rays, fortunately. But light is going to be emitted. Probably the most intense part of the sun, the solar spectrum. We get a lot of infrared, right, from the sun. feel it, the heat. Do you feel the infrared? Can you feel the infrared? You know how you can feel the infrared is you stand in the shade. If you stand in the shade and then put your arm out in the sun, let's say this is sun, do you feel that? You know, if you put your arm out in the sun, you feel the heat. But is that hot air that's hitting you? Well, if you're standing in the shade, you're cold, but you put your arm in the sun, it's warm. You know, but that's not hot air. That's infrared radiation that's hitting your arm, making it warm. How does it make it warm? Well, it causes your atoms to vibrate, increasing the kinetic energy, which increases the temperature. Does the sun emit visible? Yeah. We see white light from the sun. In fact, all the colors of the rainbow. What are the colors of the rainbow? The colors of the rainbow are Roy G. did. Red, orange, yellow, green, blue, indigo, violet. You see all those colors. Do we get ultraviolet from the sun? Yeah, we get ultraviolet as well. That's why you have to wear sunscreen. Wear sunglasses, you know. People get eye damage if they don't wear sunglasses. People are outdoors all the time. And so the sun is like a giant light bulb. So how does the sun work? Why is it a giant light bulb? What is causing all this light to be emitted? Well, it's energy. The sun is producing a lot of energy, right? The sun is producing a lot of energy, and what does that energy do? Well, what is the sun made out of? You know what the sun's made out of? Hydrogen gas. The sun's made out of hydrogen. It's a plasma. Do you know what a plasma is? What? Victor, yeah?
It goes beyond gas.
Yeah, it goes beyond a gas. You know, when we think of the sun, if you take a solid and add energy to it, what's going to happen? Eventually it's going to melt into a liquid. Liquids are higher in energy. If you take that liquid and then add energy to that, you're going to get a gas. If you take a gas and add energy to that, you're going to get a plasma. And so what happens in the sun is, normally when we think about hydrogen, hydrogen is H2. That's stable. But if we add energy to this, then what happens is the two hydrogens get broken apart, because what can happen is there could be violent collisions in the sun. There's a violent collision, boom, breaks the bond. The two hydrogens are now atomic hydrogens. Now, what can happen here is, okay, we add energy to this, and then we can excite the electrons. You know, the electrons get excited, but the electrons are still there. You know, but what can happen is, eventually the electrons get too excited. If the electrons get too excited, then we're going to have something called ionization occur. That is, the electrons actually get knocked off the atom. And so it's okay to excite the electrons as long as the electrons stay on the hydrogen, but eventually the electrons get too excited, they get knocked off the hydrogen. We call it ionization. And so what a plasma is an ionized gas. A plasma is an ionized gas. That is, you know, the collisions are so violent that it knocks electrons off the atoms. It's an ionized gas. And so what the thinking goes is like this. What happens is the electrons get excited. And so this is called an energy level diagram. Energy level diagram. And so the electrons get excited from one energy to a higher energy in the sun, because, you know, there's a lot of fusion energy. The sun is like a nuclear reactor. It's a fusion reactor, basically. And so we're going to get energy, yields energy. And so the electrons get excited, but they don't stay excited forever. You know, they get excited here eventually they drop down. These electrons will drop down in energy, but you know, what was the first law of thermodynamics? Conservation of energy. Energy is neither created nor destroyed. And so what's going to happen is, if the electron calms down, then it's going to emit energy. It's light. Emits energy is light. And so there are a whole bunch of energy levels. So we see the whole spectrum. This is called the continuous spectrum of light. Continuous spectrum of light. And the way to think about it is the electron can get excited a little bit, or can get excited a lot, or get excited to any energy in between. And so when we look at these, this is pretty much just continuous. And so wherever it ends up and then drops down, it will emit different colors of light. So if it doesn't get too excited, it will emit red light. If it gets much more excited, it will emit violet or ultraviolet light, even X-rays, depending on how excited the electron gets. And so that's what we see. And what about, well, that's the sun, but we make our own, right? We make our own light bulbs. What do we make our light bulbs out of? Well, now we have these LED light bulbs, but you know, the traditional light bulb is made up of, look at the traditional light bulb here. We call it incandescent light bulb. How do they work? Maybe this BBC version line before 14. Is there any audio? Wow. Without going into too much detail, we'll do a little demo of how an incandescent light bulb works. So if I take some metal like this, tell you. Inside an incandescent light bulb is what we call tungsten filament. So it's a piece of metal. If I heat up a piece of metal, do you know what happens? If I heat it up, it gets hot. And let's say the hot piece of metal, you hold your hand over a hot piece of metal, do you feel the heat? It's infrared. But eventually, if you get it hotter and hotter, what happens to the piece of metal? It starts to glow. Have you ever seen metal glowing red? Red hot metal? Let's see. What's on that? Stir some sticky black stuff. And so, if we look at red hot, you know, as we start to heat up the metal, it starts to glow, red hot. But if we get it even hotter and hotter, it starts to glow yellow, like this. Eventually, as it gets really, really hot, it'll start to glow like white hot. White hot is all the colors of the rainbow. And so all we're doing here is we're just heating up a piece of metal, but we aren't using a furnace. You know how they're heating this up? They're heating this up by passing electricity through here. As they pass electricity, there's a little bit of resistance, and that resistance causes heating. Things get hot, and this metal gets hotter and hotter. Well, fortunately, tungsten has a very high melting point, like tungsten. If you look at tungsten, what's tungsten next to? Tungsten is next to rhenium, osmium, iridium. All these metals have the highest melting points on there. And so tungsten, fortunately, won't melt. Other metals would melt well before they start going white hot like this, like iron. Iron's going to melt before you get it white hot, but tungsten doesn't. And so tungsten, this is just a very hot piece of tungsten. But one thing about tungsten is, and all metals are susceptible to oxidation. And so do you know inside, is there any air inside this? Now, because if air gets inside this, that metal filament will oxidize immediately and turn into metal oxide. Metal oxide doesn't conduct electricity. Metal oxide is brittle. Metal oxide will break. And so if there's and so what's inside here is an oxygen-free atmosphere. Inside here, it's like, I don't know, you want something cheap like nitrogen. Sometimes the metal atoms evaporate off the surface. If metal atoms evaporate off the surface, then they deposit on the inside surface of the bulb, which reduces light time, reduces the brightness. So sometimes what they'll do is they'll put some halogen in here. They'll make a halogen light bulb. Halogens, what they do is the halogens react with the metal that's deposited here and redeposits over there. And so it just extends the light and the brightness of it. But basically, this is it. Now, in the tungsten, what's happening in the tungsten? What's happening in the tungsten is the same thing. You know, in the tungsten metal, what's the symbol for tungsten? W. And so let's take a look. Let's say this is tungsten metal. And what happens is the electrons get excited. There's electrons in the tungsten metal. And normally, let's say at room temperature, the electrons are like this, but you know, the electrons are going to get excited. They can get excited to higher and higher energies. You don't want to excite them too much, because if you excite them too much, what will they start to emit? Ultraviolet. So you don't want to excite them too much. You don't want too much ultraviolet, but you do want visible. And so you can excite it, and you're also going to get infrared, even though you might not want infrared, you're going to get infrared. And so we're going to excite the electron to different energies. In fact, this is going to be a continuous spectrum. Continuous spectrum. Of energies and colors. So what we're going to see is we're going to see white light being emitted from here. White light. As we get excited. So for example, you can excite the electron a little bit, or you can excite it a lot. Does that make sense? And the electrons don't stay excited forever. Eventually they're going to calm down and they're going to emit the light. Energy is conserved by the first law. That's how light bulbs work. Okay, so what is a continuous spectrum? Continuous spectrum is just a continuous band of colors or continuous band of light that results for range wavelength. Continuous spectrum. Sometimes we don't see continuous spectrum. Sometimes only certain colors of light are emitted. if only certain colors of light are emitted, sometimes we'll call that line spectrum rather than continuous spectrum. These are discrete lines that occur. We'll get into this in a little bit more detail later. There's too much stuff on this slide. So what's this showing? Lambda. What's lambda called? Wavelength. A shorter wavelength, longer wavelength. This is how we can analyze the continuous. So when we get the continuous spectrum, white light here, we can separate it into its individual colors, red or violet, using a prism or diffraction grating. A prism or diffraction grating would separate it into red, orange, yellow. Red would be the longest wavelength, lowest energy. Violet over here would be the shortest wavelength, highest frequency, highest energy. That's continuous. So what the physicists did was this. The physicists tried to make a light bulb out of hydrogen. Can you make a light bulb out of hydrogen? Should be able to. What's the sun made out of? Hydrogen. So we should be able to make a hydrogen light bulb. How do we make a hydrogen light bulb? Well, we aren't going to make it like the sun. We aren't going to set up a fusion reactor, and do a nuclear reaction like the sun. Instead, you know what they're going to do? You're going to pass electricity through the hydrogen gas. Passing electricity through the gas is like a lightning bolt. You set up a lightning bulb. We could set up a lightning bolt in air. But take a look at that. When you set up a lightning bolt through air, what's going to happen? You're going to excite the electrons there, and the electrons are going to be excited to lots of different energies. And in this case, they're emitting what color light? White light. But when you set up a lightning bolt like this, because of all the collisions and whatnot, this is not going to make a great light bulb. It's going to fluctuate in intensity. So what we need to do is we need to calm the lightning bolt down. One way to calm the lightning bolt down is to lower the pressure of the gas. If we lower the pressure of the gas, then you aren't going to have as many collisions causing this kind of pattern. And so what you can do is you can make a more controlled lightning bolt just by lowering the pressure. And so what's in this tube is low pressure hydrogen gas. And then the lightning bolt is we just hook up a power supply here, high voltage. This only requires about 5,000 volts. The lightning bolt in the video was a lot higher. And then what we generate is a very nice lightning bolt like this, but this lightning bolt is not the same kind of lightning bolt, but it's similar. And this lightning bolt, it's not the electrons. In the previous one, it's the electrons. What we're trying to do is we're going to try to excite the electrons in the hydrogen atom. Now, hydrogen, like tungsten has excitable electrons. So we could excite the electrons in tungsten and generate white light. And so we should be able to do the same thing with the hydrogen atoms. The hydrogen atoms consist of one proton and one electron. So hydrogen atom has one proton and one electron. And so we should be able to excite that electron to any energy, right? It could be low energy or it could be high energy. One way of thinking about this, and some people think about the electrons orbiting around here. And so the electron can be excited to a higher speed or higher orbit, like this, or lower speed, lower orbit. The higher the speed of this electron, the bigger the orbit. That's one way that people used to think. In fact, the early physicists used to think this way. That these electrons orbited around there. Now, the thing about the electron is, can the electron go any speed it wants? So it could go slow or it could go fast. Are there any like illegal speeds for the electron? What do you think? Well, 0 is illegal, yeah. Are there any other illegal? Like, say, for example, 25 miles an hour is legal, but 25.1 miles per hour is over the speed limit, it's illegal. What do you think? Should an electron be restricted to certain speeds for safety purposes? Yeah? Or can the electron go any speed it wants, as long as you get excited? In other words, can we, give it a little bit of energy, and then a little bit of more energy, and a little bit more energy? In other words, this. When you drive your car, let's say you have a car, can you drive any speed between 0 and the maximum speed of the car, or are there certain speeds that are forbidden, like your car will not allow you to drive? Like, say, your car can drive 25 miles an hour, but the car refuses to drive at 25.1 miles per hour. Is that the case? Or can you drive 25.1? It's an artificial speed limit. Those are artificial speed limits. Your car can drive. In fact, what you have is you have a continuous spectrum, that is a continuous range of speeds your car can drive, anywhere from 0 to the maximum speed of the car. We call that continuous. Right? Continuous meaning that there's nothing forbidden. And so the same thing with this electron. The electron, like the car, it should be able to go any speed it wants, up to the max. So any speed it wants. And that's what the physicists, the early physicists predicted that. The early physicists predicted that the electron can go 60 miles an hour. It could go any speed, 60.1, 60.11, etc. But that's not what was observed. There were forbidden speeds for the electron. That is, this would be like this. Your car can drive 0 or it could drive 25, but it can't drive anything between 0 and 25. It turned out in the visible spectrum, there are only 4 allowed speeds, electrons. And so if I'm an electron here, I can get excited to this level here and drop back down. If I drop back down, then red line is emitted. And this red line has a very, very specific energy. What is that energy? That's not the power. Red line, I can tell you what that energy is. This is it here. About 600 something, 650 something, 660. In fact, we can get that pinpointed here by looking at the number. Visible spectrum for hydrogen. The wavelength, lambda, is 656 nanometers. Not 657, not 655, that's just 656. The next place it could get excited to is up here. And so electron can get excited to a little higher energy, and then when it drops back down here, it emits a green line. With a lambda equal to 486 nanometers. Nanometer would be 10 to the minus 9 meters. Then another one here, electron can get excited to a higher energy level and drop back down. and emits a blue line at lambda 434 nanometers. And then finally, there's one more up here. Electron's going to get excited all the way up here and then drop back down. If it drops back down, it emits a violet line at 410 nanometers. And so what that means is that anything between these lines is a forbidden, no-go zone for the electron. The electron cannot go anywhere in between these lines. Here. It's called forbidden. Which is weird, because in the tungsten, if we go back to the tungsten light bulb, you know, all these were allowed because we got the full rainbow of colors. In the tungsten light bulb, we have any level, the electron could go to any level it wants. That's continuous. And so one way of thinking about this is like this. All these blacked out regions are forbidden. So we see this red here, the green, the blue, the violet. Forbidden, 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 forbidden. 4 are allowed. Everything else is forbidden. So this is the way we think. If we think about the gravitational energy, we can go to any gravitational energy we want. Here, this is a continuous spectrum of gravitational potential energy, from low gravitational potential energy to high gravitational potential energy. And so we have a continuous spectrum of gravitational potential energy. What we're observing over here is there are only 4 allowed energies here for the electron. So the electron can be at this energy, or this energy. So we can think of this as floors. Electron can be on the first floor, the second floor, but it cannot be anywhere in between. Those are forbidden. So the question is why? I mean, is that because we have a proton, we have electron? What is causing the electron to be forbidden out of these? So it would be the same thing as, okay, you could drive at 25 miles an hour and 35 miles an hour, but nothing in between. What is causing those forbidden regions? So your car can move at that speed or that speed, but nothing in between. This is called continuous here. This is called quantized here. And so what we see is we see quantized energy levels. It can be at this step, or this step, or this step, but nothing in between. Whereas for the sun is a continuous. It can be at any step it wants, any height it wants, it can go. The tungsten light bulb, that could go at any height it wants. But the hydrogen lamp that we make here, which are trying to mimic the sun's hydrogen lamp, it doesn't work. It was a great idea, make a hydrogen lamp. Make it like the sun. That way we get natural light. Right? But if you tried to read using this light bulb, it's going to look awful. You know what it looks like? When you add up these 4 colors, if you add up all the colors of the rainbow, we get white light. But if you add up only these 4 colors, then the light coming off this looks like this. It's like this purple light. It looks awful. You definitely would not want a light bulb like this. All right, so that's what we call an unusual light pattern. It's unusual in the sense that it was not predicted by physics at that time. Physics at that time predicted that the hydrogen lamp should emit white light. This thing should emit white light like the tungsten filament. And so there was no physics at the time to to describe these observations, the fundamental level. So what had to happen was, this happened in the early 1900s. In the early 1900s, the physicists had to go back to the drawing board and rethink physics altogether, because couldn't explain something like this. I mean, how do you explain it? How do you explain it? You know, you would think the early physicists thought the electrons orbited around the nucleus. So if you think about it, you could make a lower energy orbit or a higher energy orbit or any orbit in between. And so the physicists, they predicted the continuous spectrum. They observed the quantized spectrum. And so the physicists went back to the drawing board. They didn't have to abandon classical physics altogether, but they had to develop a new physics. And the new physics, you know what it was called? This new physics? Quantum physics. They had to develop quantum physics. Yeah, quantum physics comes from all this. Quantum physics is the fundamental description of this observation. You know, this is observation. This observation, we got to hypothesize. Why do we see this observation? You know, because science starts off. This is the development of quantum physics. The theory that we call quantum theory came from observation. What observation did quantum theory come from? This. This was the observation that led to quantum theory. This observation led to quantum theory. So we see patterns, try to describe those patterns mathematically, and then come up with a more fundamental description of what's happening. And so this is an unusual light pattern. This is line spectrum, and so that's what they were talking about here. What was predicted was the continuous spectrum. This was what was predicted. What was observed was a line spectrum. Line spectrum means there's forbidden and allowed. Why were certain energies forbidden? Classical physics couldn't explain it. There are discrete lines in the line spectrum. Discrete lines meaning this is at 656. There's a whole rainbow of red colors from different shades of red, but only this shade was allowed, 656. The shade at 655 and the shade at 657 were not. Those were forbidden. It turns out not just hydrogen, but all the elements have a unique line spectrum. If it was just for hydrogen and everything else behaved as they did, then you think so. But there was a difference between, let's say, tungsten atoms versus tungsten metal. Tungsten atoms emit a line spectrum. Tungsten metal emits a continuous spectrum. The sun emits a continuous spectrum. The hydrogen atoms in that light bulb emit a line spectrum. And so what the difference is this. The line spectrum results when electrons are confined to an atom. When the electrons are not confined to an atom, like in tungsten metal, electrons are free to move about in the metal. In the sun, the electrons have been ionized off the atoms, so the electrons are free. They're free to move. If they're free to move, can they move at any speed they want? If you have a free electron, it can move at any speed it wants, from slow to very fast, right? And anything in between. And so in tungsten metal, that electron's not confined. It can move any speed it wants. In the sun, the electrons are not confined, they're free electrons. They can move at any speed. But in the hydrogen lamp, the electrons were confined to the atom. And so in a hydrogen lamp, the electrons being confined to the atom, they're not free to move any speed they want. And in tungsten atoms in the line spectrum, the electrons are confined to the atom. And so it has to do with electrons being confined to an atom that makes them behave. Right? And so we could see the same thing here. If we try to make a mercury light bulb, we see lines like this, discrete lines. So there are a whole bunch of forbidden energies and allowed energies, more allowed energies here. If we look at neon, this is the pattern that we see. So based on these patterns, can you come up with a theory? Quantum theory? How do you think quantum theory was developed? Was quantum theory developed because somebody all of a sudden had this idea, quantum theory, or no, it followed the scientific method. What were the steps of the scientific method again? Observation. And so these patterns were the start. And so we go from observation to patterns. Do you see the mathematical pattern here? Maybe, maybe not. It turns out there's simple mathematical equation that describes these lines here. We'll talk about that later. Here it's more complex. And then we go to some kind of hypothesis. And then we go to theory. Well, I'm going to skip a lot of the history of quantum mechanics and go right to the first theory. But we'll take a break right now and then talk about